All right, welcome back. What we're going to do in this video is to take on problems 10, 11, and 12, which are all fairly short problems. They're the kind of problems that you look for in an exam because you can do them fairly quickly. I believe it's only chapter 11, or problem 11, that requires any type of calculation. So so you're able to pick up some time that you can apply to some of the more difficult problems. Oh, by the way, problems 13 and 14 are coming up, and they're very difficult problems. Here's problem 10. Problem 10 says, which of the following statements is true? The first says, the center of confidence interval is a population parameter. Patently false. Right? The center of a confidence interval is always a point estimate. You start a confidence interval with a point estimate. It's actually what it is a sample that you have taken. Right? If you're doing means, take a sample. X bar is your best point estimate at that time, and then you paste margins of error on either side of the point estimate. So that's the center of the confidence interval. Second says, the bigger the margin of error, the smaller the confidence interval. Patently false. If you want more and more confidence, give yourself a wider and wider interval. Remember, the other way to say that is that E, the margin of error, is proportional to Z alpha over 2, and that Z alpha over 2 is associated with the confidence, directly associated with the confidence. 3 says the confidence interval is a type of point estimate. No, it's not. A confidence interval is a better estimate than a point estimate in as much as it gives you some idea of the accuracy of the estimate that you're making. And finally, gosh, we're looking for a true statement. We haven't found one yet. Population mean is an example of a point estimate. No, it's not. Population mean is a parameter. You make a point estimate of that parameter. So none of these are true, and sure enough, you've got an answer that says none of these. So I'm going to fade out, pretend I went someplace, and come right back. And I'm back. Here comes problem 11. Problem 11 says, Lauren is enrolled in a very large college calculus class. On the first exam, the class mean was 75. Let's get this down. In the first exam, we've got a mean and we've got a standard deviation. In the first exam, the mean was 75 and the standard deviation was 10. In the second exam, I feel like I'm doing something by writing something up here. The class mean was 70 and the standard deviation was 15. Lauren scored 85 on both exams. The question is, on which exam did she do better? Lauren's score was 85, so let's give me a little space here. Here's Lauren's score. It's 85. And I want to compare these two. How do I do that? Let's turn them into z-scores, right? Z-scores do just that. They take, both of these were means and standard deviations of normal distributions, two different normal distributions, one centered, if you will, on 75, one on 70. If we want to compare them, we transform all of this to a standard normal. And you do that by finding the z-score of each one. And the z-score, what the heck is the z-score? It's Lauren's score minus the mean divided by the standard deviation. And same thing here, Lauren's score minus the mean divided by the standard deviation. Yeah, so maybe you can see that I've done this wrong. No, I haven't. 85 minus 75 is 10 divided by 10 is equal to 1. 85 minus 70 is 15 divided by 15 is equal to 1. The z-score of both of these scores in these distributions is the same. She scored about equally well on both exams is the answer. All right, I'm going to take a second to erase the board. We'll finish off problem 12. So let me read problem 12 to you here. It says a manager of a factory wants to compare the mean number of units assembled per employee in a week for 2 new assembly techniques, okay? So it wants to find the number of units per employee per week for 2 different assembly techniques. 200 employees from the factory are randomly selected, and each is randomly assigned to one of the 2 techniques. And after teaching 100 employees one technique and 100 employees the other technique, the manager records the number of units each of the employees assemble in a week. Which of the following would be the most appropriate inferential statistic in this situation? Would it be a 1 sample test or would it be a 2 sample test, I think is the first thing you're asking. And what he's done is taken 2 samples, right? 100 employees with technique 1, 100 employees with technique 2. Right, so if it's anything, it's got to be a 2 sample test, which eliminates answer A and answer E, which are both 1 sample z-test and t-test. Problem C says, is it a paired t-test? Well, there's nothing paired here. Now, if you had taken 100 married couples and had the men put one thing together and had the women put another thing together, a much better and funnier test, I'm sure. Then you could match pairs, but there's no matching between the 100 employees here and the 100 employees there, so it's not a matched test. Is it a chi-squared goodness of fit test? Oh my goodness, no. All right, goodness of fit is about testing to see whether a trend in the data looks like a theoretical trend. Completely different story. So the only thing you're left with is a 2 sample t-test, and if you want to do a little check on that, why the heck do we pick a t-test? We don't have any standard deviations, do we? If we had population standard deviations known, we would have done a 2 sample z-test. Without them, this is a 2 sample t-test. Okay, let's go ahead and get ready to look at problem 13, one of the more difficult problems in this group. See you then.